So we're kind of getting into a groove here, and let me just make some observations about the pattern that we're trying to establish here. That successive operations follow commas. So if you have an operation you just in front of it is a comma, then that tells you that this operation is a successor. It's a successor of the one that's previously stood after that comma. Limit operations follow arrows. So if you look at some operation that has an arrow in front of it, that's telling you that that's a limit operation. Limits of limit operations follow two or perhaps more consecutive arrows. So in other words, this here, for example, here's something which has an arrow in front of it, but the one in front of it has an arrow in front of it. So there's actually two consecutive arrows here in front of this one here. As opposed to in front of here, there's only one consecutive arrow before that with a comma. So here there's two consecutive arrows in front of that. That's telling us that this is a higher kind of operation. It's a limit of limits operation. Right. So far we have star n squared, think of that form, and star 2n squared. Okay, so that's what exercise for you now to perhaps pause if you're interested in this business. Pause and sort of stare at this and absorb it. It's rather subtle. There's a subtle but sort of elegant pattern here, and it's plenty for you to continue this, just to write down what the next terms are going to be, see how far you can extend this. Well, why don't we be a little bit more efficient? We've seen that it's rather unnecessary to keep repeating these stars all the time, because each of these are operations, and they have subscripts. So really we only need to take care of the subscripts. We need to record the subscripts, and let's do that. And let's start in that spirit by agreeing that this addition operation might be associated with subscript 0. That's sort of consistent with what we're doing. Okay, so here is again a rewrite of what we just done. And now we can write a little bit bigger because we have a longer subscript. So we have 0, then we have 1, 2, 3 with no n. Then n plus 1, n plus 2, n plus 3, and 2. You could expect that eventually we would get n to the 4th, and then eventually n to the 5th, and so on. So there's another pattern of these things where we have successive powers of n. But that's already identified at this level here. There's the first one, there's the second one, there's the third one. So those three are already going to generate a new sequence which has limits n to the n. That's a natural limit of n squared, n cubed, n to the n. Now, how many circles should we put around that one? Not 1, not 2, not 3. We should put perhaps 10 circles around that. Well, n is just a symbol, so we should forget about the number of circles and rather think about the level or the index of the circles. So this is level 1, this is level 2, this is level 3, this is level n. Okay, so this is very analogous to what we're doing up here. Starting with something at level 1, then level 2, then level 3, and then the next one in sequence or something at level n. So this suggests that as we keep going here, we could create new and new fellows whose levels themselves reflect these ones here. So that eventually we're going to get something which will be the first thing of level n plus 1, and then level n plus 2, and then level n plus 3, and then something of level 2n, and so on. So very interesting news about at this stage here, suggesting also that there's really expansion of interest and subtlety as we're proceeding here. Things are getting more and more interesting, and this tower that we're creating somehow is reflected in the first part of this. So I'm going to leave it to you as a great exercise to explore what happens as we carry on this way. And of course, to a certain extent, it's making arbitrary, just decisions that we're making about which sequences to consider these suitable ones. But think if you play around with it for a while, you'll start to convince yourself that there's something God-given about this. It's not just me making up stuff. That there's some natural progression here that carries on, at least to a certain level. So we'll talk more about how this can carry on, but in the meantime, it's good for you to think about how this can yourselves. For practice in some kind of abstract, mathematical, maybe almost computational, mathematical investigation. Good day, I'm Norman Wapner. Today we're going to introduce a fascinating structure in mathematics, which I like to call the successor limit hierarchy. And we're introducing this in the context of these operations that we've been talking about in order to get bigger and bigger numbers. But in fact, the sort of structure of this successor limit hierarchy transcends this particular application and has connection with other branches of mathematics. In particular, it's intimately connected with a branch of modern set theory having to do with ordinals. Now, I don't believe in modern set theory, I don't believe in the usual theory of ordinals, but nevertheless, there's still some connection between what we're doing here, which is reasonably solid, and that maybe more dubious theory of ordinals. We'll talk about that later. We'll also see that this successor limit hierarchy has a very, very profound application to our understanding of numbers and infinities. It also turns out to infinitesimals. That's going to get down the road a little bit, but this is some laying some groundwork for that. So, one starting point is this idea of a successor of an operation. So if we have an arithmetical operation, say, circle cross, this could be addition or multiplication or exponentiation, or that's something quite different. It's an operation on natural numbers. We're going to find its successor, circle cross prime, in this fashion, which is not familiar to you now. So m circle cross prime 1 is by definition m, and then there's an inductive or recursive definition defining m circle cross prime n plus 1 in terms of m circle cross prime of n, as well as the previous operation circle cross. Okay, so starting with addition, we see that this way we can build up first multiplication, and then exponentiation, and then this triangle operator, the square operator, and then higher operator by just taking the successor of the previous one. So then we have something that's outside of the successor operation, another way of getting a new operation. And this involves what we might call a limit, but it's quite a different kind of limit from the usual one studied in analysis. We're using the same term, but maybe it would be better if we had some different term, but we'll use the same term limit. And so we have this particular sequence of operations, starting with star 1 of multiplication, and then star 2 which is exponentiation, star 3 which is the triangle operator, and so on. And from this sequence of operations, we conjure up a new operation called star infinity. And an alternate name for star infinity that we're going to use is star n. So this n now is just a little letter n in the alphabet, and we're just going to employ it this way. You'll see the reason for that shortly. Okay, what's the definition of this thing? Here's the definition. That if m and k are natural numbers, then m star n k is m star k k. In other words, we use the second number, the exponent, to determine the index of the star. So we're choosing the operation in this list, which is determined by this second number, star k. And then we're just taking m star k k, the product of these two numbers with respect to this particular operation. So the k is somehow being used in two different places. It's a kind of diagonal of limit operations we see. Okay, so these are the two main ingredients, and now we're going to build up a hierarchy of operations. And this is a very interesting, powerful, and somewhat mysterious way of getting enormously big structures, enormously big numbers, enormously big operations. Okay, so the idea is that we have these two different ways of building new operations, successors and limits. And even though we're going to build a successor and limit hierarchy of arithmetic operations. So if circle cross is pretty much any operation, we can always take a successor. Now limits is a little bit more subtle. If we had a particular sequence of operations that we've defined, then we can form this sort of infinite kind of limit of these sequences in exactly the same way as we've just done for the case of star 1, star 2, star 3. Of course, we'd like to be able to do this in a way that doesn't involve us having to get into this naughty realm of what we mean by infinite sequences. So what we're saying here is a kind of informal description of this process, and we are to hope that down the road we can formalize it and make it very clear what's going on, so step by step, without actually invoking anything that's infinite. Now, before we get into that, I'd like to take a little time to explain a particular very special case, and that is a situation where we're looking at multiples of powers of 1, where we're multiplying two of our objects with one of our operations, and the first one happens to be 1. So let's have a look at the first star operator, star 1, which is multiplication. 1 star 1k, which is 1 times k, is actually k. That's actually rather special, because all of the other ones, we get something different. So 1 star 2k is 1 2k, that's 1. 1 star 3k is 1 triangle k, that's 1 to the 1 to the 1 k times, that's also 1. And in fact, that's the pattern that happens from then on. So you'll remember that if L is bigger than 1, then 1 star LK equals 1 for any k natural number. This is a very simple looking formula, but it is rather subtle because there's actually two variables floating around here. There's a L, which we're assuming is bigger than 1, and of course a natural number, and there's also k. So we're asserting something being true for both L and k. So what we're going to do is going to prove this by induction. It's one of our first examples of induction. It's a rather sophisticated example, actually. So the idea is that we're going to, say, prove this for all L in the range of 2. So we're going to prove true first for L equals 2. And we'll note that when L is equal to 2, then we're going to, in that case, 1 star 2k is indeed equal to 1 for any k natural number. So it's true for L equals 2. And now we're going to assume it's true for some L, which is in the range that we're interested in, which is bigger than 1. And the aim is, by the end of the argument, we should have proven it for L plus 1. So it requires us to go from knowing that it's true for L to deducing that it's true for L plus 1. The basic inductive step. That mimics our construction of natural numbers, starting with 1 or in case 2, and proceeding one at a time to get wherever we want to go. Okay, so we're going to assume that this statement is true for some particular L. And now let's look at L plus 1. So the first thing to do with L plus 1 is look at a special case when k equals 1. 1 star L plus 1, 1. Well, notice that is equal to 1. Now what about 1 star L plus 1, k plus 1? In order to see what this is, we use the definition of the recursive or inductive aspect of star L plus 1. This is by definition 1 star L acting on 1 star L plus 1K. That's our definition of how we go from star L to star L plus 1. Okay, so the claim that 1 star L plus 1K equals 1 for K in natural numbers, this is true by induction on K, because, so let's say we're just interested in this claim that 1 star L plus 1K equals 1 for all K in N. Tails now fixed. So it's true for K equals 1, and if it's true for K, then this is going to be equal to 1, and then this is going to be equal to 1, and then this is going to be equal to 1. So if it's true for K, then it's true for K plus 1. So it's true by induction on K. So we've proven that 1 star L plus 1K equals 1 for all K natural numbers. That's exactly what we wanted to do. We wanted to go from this statement to this statement, and we've done that, and so we've satisfied the inductive step for L, and so the limit is true by induction on L. A little bit sophisticated, so if you look at complicated, how to think about it, it is a rather sophisticated notion of induction, even though the actual result is relatively simple. But we will talk about induction some more. It's very important to that kind of argument. And this is an introduction, I think we will be talking about some other cases as well. So this is just getting out what happens to powers or in fact multiples of 1 for any of our star sub K operations. Alright, so let's build up this successor limit. Alright, let's begin. We started with this basic sequence of operations. The star 1, star 2, star 3, which also became from addition, successor, and then we use this sequence to generate this star infinity, what we call star n. Now the possibility arises that we can take this star n, which is after all just an operation on natural numbers, and we can take a successor, because we can take a successor of a operation. So the successor of star n is defined the following way. And I'm going to now use m and k's instead of m and n's, because the n now is reserved for being this index underneath this operation. So previously in our various formulas we had m star something times n, okay? And now we're going to with m star something times k. Okay, so m star n prime, the successor of this one, 1 equal to m. That's always what we do. And here's the inductive step that defines m star n prime k plus 1 in terms of m star n prime k, as well as the previous operations of this star n. So there's a star n there. Okay, and now we're going to introduce some interesting notation for this successor of star n. We're going to give it another name. We're going to call it star n plus 1. So star n plus 1 is by definition the successor of star n. Star n was defined in terms of the limit of these operations. Star n plus 1 is now defined as the successor of star n. So let's see if we can get our head around this new operation, star n plus 1, by just having a look at some simple examples. So 3 star n plus 1, 1, that's always 3. 3 star n plus 1, 2. Alright, so we're just going to systematically look at the definition. This is by definition 3 star n times 3 star n plus 1, 1. So we lower this thing here by 1 there, and we lower this entry by 1 there. Now, what is 3 star n plus 1, 1? Well, 3 star anything 1 is equal to 3. So this becomes 3 star n, 3. And what is 3 star n, 3? Well, star n is star 2 star 3. And when we multiply star n, 3, what we have to do is we have to replace this n with this second entry, which happens to be a 3. So we get 3 star 3, 3. Now star 3 is our third exponentiation operator. That's our triangle operation. So this is just 3 triangle 3, which we know is 3 to the 3 to the 3, or 3 to the 27. So that's 3 star n plus 1, 2. And what about 3 star n plus 1, 3? Well, that'll be 3 star n, 1 less than this one. Followed by 3 star n plus 1, 2, 1 less than this. Okay, now this is just what we calculated. We calculated this thing here is 3 to the 27. So this is altogether 3 star n times 3 to the 27. Now the same kind of thing happens as before. This is a star n, that's a limit operation. So when we multiply this times this with respect to that, we have to replace the n with the second entry. So we get 3 star 3 to the 27 times 3 to the 27. Now this is interesting because remember that when we start considering these various stars, going past 3, 4, 5, and so on, we end up with these towers of exponentials, and we have a string of towers going this way, and then a bunch of braces of such strings going that way, and then another family of them going that way, and then another family of these bigger ones going that way, and so on. So we just going this way, and then this way, and this way, and this way. So it runs for each one of these index values. So if we have 3 to the 27, we're doing that operation many, many times. So it's a huge array. This is some enormously huge number. Much, much bigger than Gen 5 than we had 2 videos ago. Okay, let's just have a look at what the next one would be. 3 star n plus 1, 4. So again, by definition, that's 3 star n, and then multiplied by 3 star n plus 1, 3. That should be a 3. That should be a 3. There we go. And so what we're getting here is what we just calculated at the previous step, which is this 3 star 3 to the 27, 3 to the 27. And now we still have the star n here, so we have to replace the n here with this second sort of exponent. So here is 3 star 3 to the 27, 3 to the 27. That whole thing is the subscript under the star now. And then we have to again multiply that by the same thing here. So it's a similar kind of thing as we had here, except that the huge number that we take here is now the index for our star here, as well as being the exponent here, the second one. So this is vastly bigger than this one. It's almost incomprehensible how big this is. But in this early days, this is still relatively modest compared to the things we're going to be seeing shortly. Great, so now we can go further, we can extend our hierarchy. We've had this row already, and now we can take the successor of star n to get star n plus 1. And there's no reason why we can now not take the successor of star n plus 1 to get star n plus 2, let's say. And the successor of star n plus 2 is star n plus 3, and so on. So we get a new sequence of operations, so it builds from star n in a similar kind of way as these original ones were built from plus. And now a new idea suggests itself that we can take the limit of this new sequence. So the sequence star n plus 1, star n plus 2, star n plus 3 also has a limit, and we're going to give that the name star 2n. Okay, so let's have a look at what that means in terms of a limit. The actual definition doesn't have any kind of limits involved. Okay, it's important to realize that. But we're not taking something into the process here. We're not having to do something infinitely like a limit in analysis. So it's not a limit like an analysis. But nevertheless, we're still using that word, so confusion could possibly arise. So the definition here is very, very concrete. Star to n. We're defining this operation very concretely. Here's a natural number m, here's a natural number k. I'm telling you how to multiply m with k with this operation star to n. Okay, so the definition is that what you do is take this k and you square with n plus k. In other words, you go to the case operation in the sequence that defines the limit. And you choose that case one. So here's the first one, here's the second one, here's the third one. The case one is star n plus k. So we take that case operation that defines our limit, and we apply that operation to both m and k. So we define star 2n now in terms of a previous operation. But which previous operation it is depends on k. So for example, if you have factor 10 star 2n 3, then that's the definition 10 star n plus 3 times 3. And because simplify that, because this is a successor of n plus 2, so we write this as 10 star n plus 2 times 10 star n plus 3, and then subtract here 2. And we can then start going try to unravel what this thing is. It might take us quite a long time to unravel what it is. Okay, so now we're trying to cross convergence. That we started with our first row. We have our first limit star n. And then we took the successor of star n, we have the sequence, and we took infinite star 2n. Now we're just going to take the successor of this one, and everything else star 2n plus 1 is the first one. And then the successor of that will be star 2n plus 2, and then star 2n plus 3. Now we have a new sequence of operations. We take the limit of the sequence, and we get star 2n. And we keep going here. We keep going, and so on. So we're taking all these new limits. Let's actually make it very clear. So these are kind of new kinds of operations that are different in character, essentially different in character from these. Each one is the successor of something like on before. These ones are not successors, they're limits. And notice I have put a little colon beside them. That's some kind of notation that we can use to alert us to the fact that this thing here is actually a limit, not a successor. Okay, and now you might say, well, here's a lovely hierarchy, but because it's sort of potentially ongoing grid, we can just keep on adding more and more rows, and we can get bigger and bigger operations. Fabulous. That's good. But in this story, whenever you have some kind of pattern that you're comfortable with, you can go beyond your comfort zone. You can go to the next level. You don't want to, but you can. Okay? And in this case, going to the next level requires a shift of thinking. In fact, it almost always requires some kind of shift of thinking. You have to think in a little bit different way than you have been up to that point. So when you think a little bit differently, we're going to say, well, we created these new kinds of operations. They are limit operations rather than successor operations. Okay, so now we have a new type of sequence. Namely, these green ones here, they themselves form a sequence of operations. We can take the limits of these ones. Previously, we've just been taking limits of things along rows, and now we're taking the limits of those rows and regarding them as a column, and we're taking the limit of that. So here's star n, star 2n, star 3n. These can be used to generate a new operation called star n squared. Star n squared. Now, what is the definition of star n squared? Well, it's the same kind of thing that we've seen before. We always define a limiting operation on a sequence in the same way. So once we have our sequence clearly in mind, then the definition of the limiting operation is completely cut and dry. So m star n squared k. We're going to multiply m and k with this operation. So what do we do? Well, we regard this as being created in some limiting fashion from this sequence. And what we do is we take the kth element in the sequence. Go to the second exponent here, the second operand, and we take the kth element in the sequence. This is the first element, this is the second element, that's the third element. So the kth element will be star kn. And that's what we do to m and k. We multiply them with the operator star kn. That's already defined. It's already in existence. We're using it to multiply m and k, or we should say exponentiate m and k, whatever. Okay, so this is quite interesting now. It's a new kind of limit. It's at some point kind of a higher limit than these ones, because it's a limit of limits. So, for example, we might now ask, what is 3 star n squared 4? That's just a number. These are numbers, and this is an operation. Like exponentiation or triangle operation.